In this section, we're going to discuss algorithm discovery and design, which comes from Chapter 2. And we already went over the formal definition of an algorithm and the requirements for an algorithm. So now we're going to discuss how to represent and write algorithms. Now, actually, as an aside, I just wanted to mention, where algorithms came from. And algorithms have been around for a very long time, from probably since thousands of years ago, but they just became more formalized over the last few hundred years, particularly in the, I guess, 800 to 1200 BC time period. But it's kind of well known that there was a time when people were trying to come up with ways to solve like roots of equations and linear equations and quadratic equations, and they were using descriptions of the steps you would go through, or they had descriptions of the steps you would go through to, let's say, solve the root of a number that wasn't, for let's say, a square number. So there was a set of instructions that people would write down to actually tell you how to, or describe how to come up with that root. And this process became known more formally as an algorithm, as how to describe a way to solve a problem. And it was usually a mathematical problem. So how could you actually write the algorithm in such a way that other people can understand it? And natural language is not really the best way to go, because uh, it can be verbose depending on who's writing it, and it can sometimes lack accuracy and precision, or sometimes it could have too much information, so it's kind of hard to interpret. And so um, we don't want to use formal programming languages either, because really algorithms should be designed at a more abstract level. Programming languages will force us to deal with low-level issues of syntax. For example, like Python has a different syntax than, let's say, C++. And what I mean by syntax is like grammar, how you express the programming language. There's different rules for writing Python code than there is for C++. So there's got to be something better than that. So what we want is a more general solution to doing this, and we do this with pseudocode. So it's kind of a way, it's kind of like a programming language without the details or specific syntax that a specific language like C++ or Python would have. And it's made up of a subset of English and mathematical symbols, and it's pretty flexible. So you don't have to follow a specific type of syntax, but there's some general um, types of operations that you can do. And for the sequence control structures, there's three basic ones. There's input for getting, let's say, a value of a variable. So you might want to get some input from the user from the keyboard. And then output is just basically displaying some information or printing some information out. And then computation would be performing some sort of mathematical operation or arithmetic on a variable. Uh, oops. So here's an example of a sequence control structure. So the problem is compute the area of a rectangle, and the algorithm to do that is basically three steps. The first step is you have to get the input, so you have to get the dimension. So it would be get the length and width. I think that was just my email that went off. The second instruction would be set the area to the length times the width. So that's the formula of, the area of a rectangle. And then finally, print the area. So an algorithm generally has to have input, so you're getting some sort of input data or something like that, some sort of computation, which is your set statement there, and then some output, which is your print area statement. The selection conditional operations allow you to choose between different actions. So if the example here says if a condition is true, then do action X, otherwise do action Y. And the condition is always going to be a true or false expression. So that true or false expression helps you to figure out, or helps the algorithm or program to understand which action it needs to perform. So an example of this would be, let's say we want to get three values, x, y, and z. And the next statement is, if x is greater than 0, then you want to set the average equal to x plus y plus z divided by 3, and then print the average. Otherwise, you're going to print out bad data. So basically it's just saying that x has to be a positive number, and we're going to print the average of those three numbers. Iteration is, like we talked about before, that's a looping condition. So you're basically repeating an action within a block until a certain condition is met. So here's an example where we're counting by 2's from 0 to 10 and printing out the values. So the first statement is to set a variable called count to 0, and we're going to use this variable count to keep track of how many times to execute the loop. And so we're saying while count is less than or equal to 10, print the variable count, and then add 2 to that variable. And then after it adds the 2, it's going to go back up to the while statement and check to see if what the value of count is. So in this case, it's going to keep doing that, I guess, 5 times until it finishes, and then it's going to end the loop. And the other side, the algorithm 2 method, is basically the same thing, except the difference is it's a do while type of statement. So it means you're going to set the count to 0, and then you're going to go into this do loop and then print the count and add 2, and then you're going to check for count less than or equal to 10. So the difference is between the first and the second one. In the first one, you check that the value is less than or equal to 10 before you go into the loop. In the second one, you automatically go into the loop and then you check. So for example, if set count was set to, let's say, 12 up here, it would never go into this loop for the first algorithm. But in the second case, if you set count to 12, it would go into the do loop and do these two statements, the print count and the add 2 to count, and then it would check to see that count is not less than or equal to 10, and then it would exit out. And so a good way to keep track of algorithms and while you're dealing with these loops type of structures is to do what's called a walkthrough or trace. And basically what you're doing is you want to, just with your pen and paper, kind of keep track of the variables and what step and what the values of the variable, what changes happen to the variables at each step of the algorithm. And then you write that down, and then you can kind of follow through what's going on. So for example, the algorithm trace for the previous looping problem, we're going to have a trace for count and the output. And so we set the count equal to 0. So initially the count is equal to 0, and the output is, it's probably not going to be anything actually, so you could just have that blank instead of a 0. And then the second step, and then you've got the while statement, and then each iteration through this while statement, you want to keep track of the count and the output. And then finally, at the very end, you'll see that count is actually equal to 12, but there's no output, and that's because it's that when count is equal to 12, the while loop checks to see that that condition is not met anymore, and it exits out of the loop, and it never prints that last value out. So just a summary, that pseudocode is a flexible way to solve a problem, and you can check out the textbook to get more familiar with some examples. There's some homework exercise problems that are very good to go through to actually to put this in practice and test this out for yourself. All right, see you next time.